Hi everyone, I'm a PhD student at in Telecom Paris, as you said, and I will present what I did on my first year. So it's a work called PK clustering, and it's about integrating prior knowledge in mixed initiative social network clustering. And it's a work that I made with Paolo Bono, Jean-Daniel Fequet, Catherine Plaisant, and Paola Valdivia across multiple institution, as you can see. So it's a work we have done in collaboration with social scientists such as historians. And usually what they do is they work with raw documents mentioning people. So they have access on a corpus of documents that they study in a long time, and they try to analyze how several people behave across these documents. So usually it's a tedious data generation process, and they analyze a lot these documents, and that give typically medium-sized networks such as 200 plus nodes. And they want to do a long, careful, and detailed analysis of these documents and these people. So usually what they do is starting from this corpus of documents, they try to build social networks. So these are graphs objects. And one way to do it is to build what we call bipartite networks. So there will be two types of nodes, the person's nodes and the documents nodes. And the person nodes will connect the documents nodes if they are mentioned in these documents. So it will build one type of networks. And we use this type of networks because it is the closest representation of the raw documents. It do not use projections or things like that. So one way of visualize these types of bipartite networks that we can also call hypergraphs is to use the POV system, which has been designed to visualize these types of objects. So at the left, we have the list of persons. Each person is represented by a row. And at the right, there is a hypergraph. So each document is represented by a vertical line which connects several people between them. So at the right, we have one example, which is one document connecting three people, Guillaume, Madeleine, and Renexin in this example. So very often, when the data grows, the analysis cannot remain at the individual level of the person, and very often a higher level or a cluster level is needed to have an analysis at a higher view. So the graph clustering is a task of grouping people together to accomplish this thing of grouping people. And in this task, we want to group people such that two people in the same group are more similar between them than with people in the rest of the graph. So the similar measure or the similar concept is a bit subjective, but usually we can use, for example, topology of the graph or the attributes of the graph, if there are attributes, to group people which are more densely connected between them, or to group people who have similar characteristics according to one or several attributes. So on the right, this is an example of the same graph as before, but now clustered. So we have three groups, one blue, one red, and one green. And we can see that the people, for example, in the blue group are more connected with people in the same group than with people exterior or of their group. So there is a lot of techniques already existing for applying graph clustering. One taxonomy is to separate the existing techniques in three groups. So the automatic graph clustering method. So we will use one algorithm to produce an automatic partition of the graph. Then there are the ensemble techniques, which consist in using a lot of different algorithms and to produce an optimal final partition using the results of the automatic methods. And then there are the semi-supervised method, which will use some prior knowledge in the computation. So the algorithm will use the prior knowledge given as an input in its computation. So in these existing methods, there are several drawbacks, such as the lack of understanding on all the algorithms work very often. So for example, if we use an automatic clustering, very often we don't really know how the computation has been made, and we just use the results. Also, very often the users cannot use their prior knowledge that they can have. And in the social science, they always have some prior knowledge, but they very often cannot use it using automatic method. But semi-supervised method can use the prior knowledge, but it's the only type of method who does it. And then it's hard to review and evaluate the results with automatic methods. It takes time, and very often the users will use a lot of different algorithms, and they have to review kind of at hand, and it's a bit tedious. So in the end, it's there is always the question of what method should I use for my datasets, and there are no direct answer. So we try to answer several of these questions and problems. And for that, we propose a new approach for doing graph clustering, what we call PK clustering. And it tries to combine several aspects of the three objects in order to give more control to the user in the analysis loop. So it can be divided in three main steps. First, the user will enter some prior knowledge that he has on his data, which are partial clusters. The second main step will be the consolidation and the explanation of the prior knowledge cluster, so the groups that the user gave. And then the final step will be to consolidate extra clusters, so to explore potential new groups that the user was not particularly aware of or did not have prior knowledge on it. So as I said, the first step is the specification of the prior knowledge. So the user will enter some partial groups. So it will be small groups, usually consisting of 2 or 3, 4, or a bit more people. So in this example on the left, for example, the user specified two groups. The blue group A with Elise and Jacques, and the group B with Hubert and Vallée. So it means that she knows that Elise and Jacques are in the same group, considering her knowledge of the data, and she knows that Hubert and Vallée are in another groups different than group A. So then a bunch of implemented clustering algorithms are run on the data at the same time. And then we show the results to the user, knowing that the results are ranked by how well they match the prior knowledge which has been entered. So to do that, we compute the edit distance between the prior knowledge and the results of the clustering to have a metric of similarity between the raw results of the algorithms and the prior knowledge. So we ranked tie, and from that, the users will select algorithms she thinks are appropriate regarding to her knowledge. So on the right, we have a view according to the person, so a person view and an aggregate view at the bottom. So we can see that the 4 top algorithms gave a perfect match, and then the next algorithm give a partial match. There is Elise, which have not been matched. So she was in another group of the blue group, and then the next algorithm did not give any matching because the resulting clusters were too different of the prior knowledge groups. So the second phase of the process is in another view. So we show the graph again, and we also show the of the algorithms on the left. So at the full left, we have the consensus. So it shows at which point the algorithms agree on each person, so on each row. Then we have the results of the algorithms represented as column. So first we show the prior knowledge as a column that the users entered. And then there are all the algorithms that the user selected. And each diamond represents the result of one algorithm for one person. And then at the right, we have one column for what we call the consolidated knowledge, which is the final partition that the user will build iteratively in the process. And then at the right, there is a graph that the user can explore, trying several algorithms that she ran and selected. So on this phase, the system can give suggestions based on the consensus of the algorithms or a selected algorithm. And what the user will do is consolidate the final partition, which is the final result that the user will have, using the suggestion of the system based on the consensus or one or several specific algorithms that she's interested in. So the user can do several things. Validate the suggestions or focus on one specific algorithm she's interested in. So the circles on the consolidated knowledge will be the suggestions given by the system, either with the consensus. So if all the algorithms agree on the results for several people, for example, the system will give suggestions to validate the results on the consensual group for these people, for example. Or the system can give suggestions based on one specific algorithm that the user chose if she thinks the results are interesting considering the graph that she can see on the right. So we implemented several interaction techniques to validate the suggestions and for the system to give suggestions. So the first one is a consensus on the left. So we show the consensus of the algorithms, and the user can specify a threshold to say, for example, that she wants suggestions based on a threshold of 90%. So it means that 9 algorithms out of 10 would agree for the suggestions to appear if there are 10 selected algorithms. Then the user can copy the result of one specific algorithm and then consolidate one part of the results or all the labels, for example. And to consolidate the suggestions, so the user can click on the circles on click and drag to validate several persons at the same time. She can do the same for one specific algorithm by clicking or dragging on the diamond shapes. And finally, we allow manual labeling or manual overriding of one or several specific people by right-clicking on the consolidated knowledge column for one person and just manually assigning one label, not taking into account, for example, the results of the algorithms. So it gives the main control to the user if she knows that one specific people is classified in one specific group, for example, considering other sources that historians and social scientists often have. And then the final step will be the validation of extra clusters, because it can happen that it exists other groups than the prior knowledge groups entered by the user. If the graph is big, for example, or if the user do not have a lot of knowledge on the graph. So to do that, the user can select any of the selected algorithms. She can select the one she thinks is interesting. She can explore the results of these algorithms. And if she finds one cluster that is very interesting, she can validate it. So in the example, there is the group called 2 on the right. if she hover the label of this group, she will see how this group is consensual across the algorithms. So if a group is found across a lot of other algorithms, it will be consensual. And we can see this with the diamond shapes on the left when we hover over a specific group. If she thinks that the group is interesting, she can validate it clicking on the label and renaming it. And at this point, she will be able to consolidate these groups the same ways as the other pre-knowledge group. So using consensus or the results of one algorithm and using overweight. So at the end of the process, the user should have a consensual and satisfactory partition regarding the prior knowledge, the graph that is on the right and that you can explore, and her other sources that she can have, such as documents or other letters mentioning the same people that she's studying. We also allowed that some people can be left unlabeled if they are not very interesting considering the analysis that the scientists want to do. So since it's an interactive system, I will show you a short demo of this process using the Maribushi dataset, which is a dataset studied by by Nicole Dufourneau. I will directly. So I don't think you have the sound, so I will speak over the video. So the first step will be to enter the prior knowledge of the graph. So here the user will create two groups. The first blue group, she will put Marie Boucher and Jean Masson-Lesnay, that she call group A. In the second group, she will put Hubert Antome and Marguerite Antome, that she will call group B. Then we can launch all the clustering algorithms, which will be run on the dataset at the same time. And then we show the results ranked by how well they match the prior knowledge. So here we can see that the 6 top algorithms gave a perfect match. The two persons of the blue groups and the 2 persons of the red groups have been found together in 2 separate groups. And then the 2 next algorithms gave a partial match. We can see that with the 2 gray circle. And then the next 3 algorithms did not give any matching results at all. The results were too different. So the white squares give information on the size of the found cluster, and the squares on the right give information on the overall clusters found. So at this point, the user can review the result of one specific algorithm that she can find interesting, considering how it has been computed and the overall shapes of the cluster. And so at the left, A, B, and others are the groups found by the cluster. And when we click on others, we can see the details of the other clusters found. But very often we will want to compare the results of the different algorithms. So the algorithms who gave a perfect match are selected by default with the checkboxes. And by clicking on the review, it will select all these algorithms and show them on the system on the left. So we have the prior knowledge, the selected algorithms, and the consolidated knowledge, the final column, which we will try to build iteratively. So here we can see that there is a lot of consensus on the red persons, except the last ones, where only 3 algorithms agrees very often. And we can see that the consensus is less clear for the blue groups. So very often, not all the algorithms agree for putting people in that group together. So at this point, the user will use her sources and the graph to try to consolidate the prior knowledge group to start. She can use the consensus slider on the left to put a threshold, and it will put the suggestions are circles for the people who are consensual given the given threshold. She can then validate these suggestions by clicking or dragging on the circles. It will turn the circles into squares which means it will be validated results. Then for the less consensual persons, she can validate the results from one specific algorithms by clicking or dragging, giving the shape of the graph on the right and her knowledge. And at the end of this step, if there are still persons not labeled, she can explore the other clusters of one or several algorithms. By clicking on others, the details will appear. And now we can see, for example, that there are 5 other clusters found by the Iluvan time algorithms. And if we hover over a specific group, the detail will show of how consensual these groups are considering all the other algorithms. So if she finds this group interesting, she can click on it and rename it, and then she will be able to validate it the same way as the other groups. She also can leave some people unlabeled, and at the end, she should have consensual and satisfactory partition at the end of this process. So we know that this process can have some biases, such as users have a lot of influence on the results. They can overwrite labels, and if the pre-knowledge is wrong, the system will still suggest clustering that match it. However, we know that traditional clustering have a lot of biases as well, such as the priming bias. If as a user first try one algorithm, it will possibly bias his view of the data, for example. And very often it do not propose alternate views on the data because there is no ground truth very often, and several different partitions can coexist in the same data set. So to increase the transparency of the process, at the end we provide a summary table and a summary reports. So here is a summary table giving for each person of the graph the consolidated knowledge found at the end, the result of each algorithm selected, and the decision, so how the results have been consolidated, either by consensus, one algorithm, or manual override. So in this example, the first person, Eloy and Tom, has been consolidated using the Iluvan time algorithm. Julien Girard using the consensus of 8 or more algorithms. And Rose Boucher have been consolidated using a manual override. Here is a summary report of the use case. So there was 3 groups with 3 persons for the prior knowledge, and in the end there was 4 groups of 37 persons consolidated, and we give general statistics on how the results have been consolidated. 13 algorithms have been considered and 9 algorithms have been reviewed and compared. So we try to evaluate the system in collaboration with historians and social scientists. So the first use case we did was the dataset I showed on the demo. So it's a dataset consisting of French merchants of the 17th century, which is a dataset analyzed by Nicole Dufourneau. And the system allowed her to build this partition that I showed. She had an hypothesis that this data was split into 3 groups, mainly according time. So she used the Iluvan time algorithms to validate the suggestions, her hypothesis, plus the consensus of the algorithms. And the second use case was a scientific publication on the conference. So we had knowledge on the groups of the person according to their affiliation, and it allowed to build partition giving the general affiliation of the people and their connection. And we're still trying to evaluate the system. So with other social scientists and historian. So here is a data set that we are currently trying to evaluate with Nicoletta Rolla and Pascal Cristofoli with their data set of construction contracts in Pierremont. So we are still open to collaboration. So if you have a data set which match this use case, don't hesitate to contact us. So as a conclusion, PK clustering is a new way of doing clustering. It's a mixed initiative and interactive process which uses the prior knowledge of the user. And it reflects that several ways of clustering the data exist, which are not necessarily contradictory, because there is often no ground truth on the data, and several different partitions can coexist, which are interesting. And the system tries to assist the users in reporting and justifying their choices and intervention. And as a future work, we plan to compare the results of the algorithms more in depth between them. And we also want to explore the overlapping clustering methods and dynamic clustering and visualization method that we already started to do. Thank you for your attention, and if you have any question, don't hesitate.
So is there, do you envision to implement any mechanism that would be able to say to the user, okay, this prior knowledge that you give me is really, really improbable? Is there any way to say, yeah, this doesn't seem to work with anything?
Yeah, so yes, we thought about that, and so if the user puts some prior knowledge which is really weird, for example, usually in the ranking view, there won't be many algorithms, or even there will be no algorithms which give a match. And so this is a signal to the user that there is a high chance that the prior knowledge is clearly wrong. And it's an indication to point on that it's maybe interesting to use some another prior knowledge, but it's not it's still possible. So if the user is very sure about this, maybe it's just that the information is not reflected in the data. But viewing the matching view, we can see if the prior knowledge is in reflection to the algorithm's results.
Okay, then I'll just finish by asking, what are the use cases that you envision being the most relevant? What disciplines other than history, for example?
Well, it can use in, I think, every discipline if the user has some kind of prior knowledge on the data. So yeah, I think social science are the main use cases, because very often the historians or social scientists study some kind of data set with a lot of knowledge, and they often have other sources such as letters or books, so they often have a lot of prior knowledge, and it was a bit frustrating for them to use automatic system which do not really guide the users. But it can be used with any kind of graph data set, really. So I guess biological networks, for example, if we are sure that some biological entities such as molecule or gene are in the same group, which I think is the case for some biological data sets, and biologists would have some prior knowledge. So yes, or transportation networks if we have some constraints that we want to ensure on the clustering, it can be used. So yeah, I would say any domain really if the user have some prior knowledge. So the system won't be used for first exploration of one dataset. So if we just obtain a dataset and we want to explore it, it won't be the first use case because we won't have any prior knowledge. But it can be used in any domain if you have some kind of graph.
Okay. Well, thank you very much for presenting this very interesting tool.